a combinatorial geometric object which was some pairs of simplices in projective space and special position with respect to each other. And let me repeat the definition and maybe expand on it in a little bit. So I won't repeat what a projective simplex is. So I had a definition of what a special pair of simplices was. So PQ is a special pair. So everything leaves. I will only talk about vector spaces over fields, and whenever I talk about any kind of homology, it will be with rational coefficients, so there will be nothing complicated in that. So it's a special pair. If Q1 is P1 and Qi lies on the line between two consecutive P's, where I equal 2 up to V, and so we live in projective space over V, and dimension of V will always be D. So in the paper it's called Coxeter pairs, but the talk it doesn't matter. So there's the only problem is that there is another concept which is, I have to say, a generic special pair, which sounds kind of self-contradictory. So if in addition, well, if this hold plus Qi is not equal to Pi for I from 2 to V. Okay. So it's easier to draw a picture.
Can you clarify which of these indices are i's and which ones are ones?
Yeah, okay, sorry. So this is 1, and everything that's, well, okay, I minus 1, this is I. Yeah, this is I.
And then
these are both I.
Great, thank you. That helps.
Yeah,
It's hard to see from here.
Yeah, sorry. Probably can do something about my handwriting, so I won't. I actually forgot which color I used for which, but so the picture was basically we had the outer simplex, which is given by P's, and kind of an inner simplex, which is given by Q's. And this is all a projective picture. And so this would be an example of a generic special pair. And what are the possible degenerations? Well, what can happen is that so by definition, all of my simplices should be in general position, so I don't allow degenerating each of these simplices individually. But the relative position can be different, so what could happen is Q2 could go to P2. And that would be one type of degeneration. And in fact, all types of degenerations are described by some collection of indices for which Pi and Qi coincide. So you could have both of these things happen. And so, okay, so there was a claim that we made which may not have been exactly correct. So there is a bijection between generic special pairs. PQ are exactly the type of configurations which appear if you look at this L element that I wrote down in the isolation. So it's exactly the Pi is equal to V, well, D. So exactly the P's and Q's which can be represented by
these are sums, right?
Oh, sorry. By the same elements which appeared in the definition of L, of this L of which corresponds to multiple polylogarithms, and for some basis V1, VB. And I might have said that all special pairs are like that. So that's not the case because the degenerate ones are not of this type. But you can also describe them, and it's a pretty nice picture. So the degenerate pairs of special pairs are exactly products in the Steinberg H. So let me draw another picture just to explain what I mean. So if I degenerate Q2, if I make Q2 equal P2, so I'll have a picture like this. And so previously I had maybe a little bit where this was V3, this was V3 plus V2, this was V3 plus V2 plus V1. So that was when we had the non-degenerate situation. But here actually what I have to do is I have to split it. So this would be actually V2. And this would be V2 plus V1. And this would still be V3. So this is Q1, and this is Q1. And this would be, so this point would be V. V3, and you see that V2 is equal to V2. And so this corresponds under this kind of idea of relating it to the elements which come from polylogarithms. So this would actually be L of V1, V2 times L of V3. So I have to kind of stop writing this color. And if you do an even more degenerate configuration, so this is just an example. You have a completely general statement which is also easy to prove. So all of the degenerate special pairs are products in this Steinberg H, in this VB statement. So when you have all of the vertices coincide, you get an even more special product. So this would be L of V1 times L of V2 times L of V3. And so,
sorry, what product are you taking? What's
so this is a product. This is kind of this is in Steinberg H of V1, V2, and I'm kind of implicitly assuming that this everything lives in some space. So times Steinberg H of V3, which maps into Steinberg H of the bigger vector space.
This is the block.
Yeah, this is the block product. Yes, exactly. Okay. So this is already kind of nice because so I quotient out by some products on a polylogarithm site, and usually what one does is studies the Lie algebra of incomposables. But here we actually kept information about almost everything product-wise. So, and it's very simple combinatorial situation.
Can we maybe close the window again?
Okay, so there's a little bit more structure. I mean, there's a lot more structure. So what I want to talk about next is something very simple again, geometrically, but maybe not immediately obvious. So there is also projective duality somewhere here in place, which kind of acts on, it acts on Steinberg modules individually. It also acts on the Steinberg H, so the tensor product of two Steinbergs.
Is this a co-product or the product?
This is a product, so this is like the M, the multiple.
It's a product.
Yeah, so what you can just take this element in Steinberg, tensor Steinberg in the subspace, and this element, and just multiply them together, and you'll literally get.
Yeah, I get that. Okay, great.
Yes. So all of my pictures are not like some abstract. It's embedded in some projective space, so you can actually work out what would go on. There's duality, which, on the level of simplices. So this is projective duality. So if you have a simplex P1 to PD, you map it to a dual simplex, which is H1 up to HD. In, well, I guess projective space of V dual to the power V. And the formula is you just take the hyperplane spanned by subsets of D minus 1 here, and just define linear functionals in the projective space. And what's nice about this map is actually, so if you think about, so if I call S of P the element in the Steinberg corresponding to these lines, then, I mean, this is actually a very well-defined automorphism. Not automorphism, but it's an isomorphism between Steinberg V and Steinberg V2. So P, class of P going to class of P dual is a well-defined on Steinberg V. And so one can take this and apply the same construction to the tensor product of two Steinbergs, but there is actually several choices you can make. So if you take PQ, what you could do is you could flip one, flip the other, and what you can actually also do is you change the two simplicities. And what turns out to be the best notion for duality there is you kind of do everything. So you flip Q, flip P, and you interchange the order. And so, again, this is well defined on Steinberg H. And what happens is actually, so maybe a claim, it's a small exercise. So D maps special pairs shortcut. So we had elements which I called L of V1, VB. And we can look at what this operation does to them. So it again should give you something special. And in fact, it maps non-degenerate special pairs to non-degenerate. So it should give you somehow again L of something. And it turns out to be exactly the relation between iterated integrals and the multiple polylogarithms that I was one of the first things I did in the first lecture. So let me do.
Is this the antipode for the Hopf algebra structure? Or
Probably yes. I mean, that I don't know for sure. There's not much else you can do, so maybe that has to be the one. So if it were a monopolylogarithm, that would actually be the case, but here it's probably true, but I don't know this for sure. Okay, so this map, so I haven't defined what it does. So it actually extends L somewhere. And this is just this duality map which takes a pair of simplices and interchanges the order and dualizes. And so what is this I, and what are these upper script things? So VG, so V1 up to VG is a dual basis in the dual. And this element I, V1, so I'll use different letters. So I of W1, WD. So it's again a pair of classes in Steinberg, but I'll parameterize them differently. And again, unfortunately, the notation is reversed. That's how it goes. So it's now WD going down to W1 in reversed order. And then the second part is WD, WD, W1 minus W2. So all consecutive differences between points, between vectors WI. So again, this is Steinberg H V. And so why am I doing that? Well, actually now for every theorem that you prove in Steinberg H, you get a second theorem for free. And this will actually help quite a lot. So what I want to do now is mention some of the properties of these functions L and I.
So how are you transiting between Steinberg of V dual and Steinberg of V?
Steinberg of V dual. I think this is what I'm doing. So I'm taking any simplex. You mean what happens on the level of? I mean,
isn't P dual in Steinberg of V dual?
In P dual.
It's a map from Steinberg of V to Steinberg of V dual.
Yes.
So okay, so here when I'm writing hyperplanes here, but you should think of them as linear functionals on V dual.
Yes. So the end result is in Steinberg of V dual.
Yes.
Right. So then it's not a. So where is D a map from and to?
It's from Steinberg V to Steinberg V dual.
Okay.
Well, now here it's just a map of simplices, but when I'm writing it here, it's from Steinberg. Maybe on is misleading, so. Yeah, I mean, if you write it out as matrices, it's actually A inverse transpose. That's what this map does.
In some bases.
Yeah, in some bases. That's maybe more familiar. Okay, so there's two sets of elements, and what basically the claim is, all of the simple properties of multiple polylogarithms, you can actually just forget about what multiple polylogarithms were. There were some identities there. All of them kind of, you can see on the level of Steinberg H. And it's kind of nice and simple. And I'll give a few properties, but I don't know how much. So both L and I will satisfy a shuffle product identity. That's kind of, I mean, it's clear on the polylogarithm side, on the Steinberg module side, that actually you have to, it's a theorem that you have to prove. So if you take a product of two L's, it's a product in the VB sense. So whenever I write a dot, it will just mean there's actually a decomposition of a space into two parts, and the product is in VB sense. So it's again a sum of the shuffles. L of V sigma 1, V sigma K plus L, and this is basically the Lie shuffle product formula that we had on the polylogarithm side. And we have an exactly identical formula, which you get for free once you've proved this one. For the dual basis, and this is the shuffle product formula for the equal. And there are two different formulas. Actually, they're not directly equivalent, so you only get them after you play again.
So what you call Lie shuffle is quasi-shuffle modulo lower depth, right?
It's quasi-shuffle modulo lower depth. I mean, I won't write it. And there's no lower depth because we killed it at the very beginning. So in the Steinberg module, it's everything. Everything is depth D. And here, I mean, it's exactly the same formula, just replace L by I. So that's that, there's that. And kind of, so this is not a very simple statement, but it's something that you do whenever you have double shuffle identities. So it's a corollary. So as a corollary, you get, I haven't quite defined it yet, but here's the definition. So Steinberg L is, I think, what in previous talks would be called Steinberg infinity. So this, the co-kernel of the multiplication map. So in Steinberg H. And this is this day, sorry, not like that, but a convolution in Steinberg H, which you can write out explicitly, so you just kill off all of the products, which in particular means all of the degenerate special configurations go away, which is quite nice. And so if you look at these identities, it tells you the left-hand side is actually 0 in the Steinberg L, but on the right-hand side you get some linear relations. And it turns out that they imply, just by some combinatorial argument, a certain symmetry which is hard to see otherwise. So LL, so I'll define it kind of in a way. So I'll define first a function on sets of vectors with sum 0. And I will map it to L of V1, Vn in this, in the composable part. So this is in Steinberg. And the claim is this function of n plus 1 tuples of vectors with sum 0. It's dihedrally symmetric in the shifts of the indices. So it's dihedrally symmetric in Vn mod n plus 1z. So what it means that if you think of this as a function on circles, where the labels of n plus 1 points are the vectors and the sum is 0, then this has all the natural symmetries that you have in this picture. So all the rotations, they preserve the value. And if you flip it, it also is preserved. So that's nice. And for the price of, well, not doing any more work. So this is kind of an abstract result that follows once you have double shuffle. And for the E functions, the actual symmetry is different, but it's again cyclic symmetry. So here, you take all the n modulo diagonal translations, I guess. And so it's like V plus 1 modulo diagonal V. And here you map V0, Vn in a different way. So you map it to IL of V1 minus V0, Vn minus V0. And this is again dihedrally symmetric. So it kind of looks like, because there's no difference between these two formulas, that actually the symmetries you should get are the same, but actually they're not. So the dual of this type of symmetry is actually slightly different. Okay, so this particular part will be quite important.
What is the statement versus the definition here?
Okay, so I would say that if you call this function maybe phi, then phi of V0, Vn is equal to phi of V1, Vn, V0. That's one of the statements. The other one is equal to phi of Vn, V0. So you can both reverse the order and then cyclically permute the things. Yeah. So this is what I mean by this, the dihedral symmetry. Okay. So there's a few other things that one can prove. And all of these are purely combinatorial statements that you just prove in the Steinberg module. So there's no polylogarithms involved anywhere. So if you don't like polylogarithms actually, and if you like Steinberg module, that would be a good replacement. And it seems to kind of carry along a lot of structure. So it gives a good idea of what's going on. So, so I want to talk about the theorem that I started with. So there were two parts in the theorem. One was the map was injective, and the other was the map was surjective. So I want to talk about the surjectivity. Because that's kind of a statement purely about the Steinberg module. Well, Steinberg H. So surjectivity. If you just read off what surjectivity means, it would imply that Steinberg HV is generated by L1 as you run over all possible tuples of vectors. Yes, no, all possible bases. If V1 up to Vd doesn't form a basis, we just call this element 0. So now how to prove this, and actually what's going on here, and that's the main point. So there's two theorems. So I want to prove two statements which are slightly stronger than just surjectivity. But I will prove it first on the level of special pairs. So if I had special pairs, simply this is before, I haven't defined this notation yet, but I will just call S of a pair of simplices is the product of the corresponding apartments in Steinberg H. So I want to prove, well, I'll formulate two theorems and then I'll draw some pictures and hopefully you'll be convinced that they're true. So there will be a theorem and theorem dual. And the theorem tells you that if you fix a hyperplane, then S of PQ as PQ runs over special pairs with an additional property. Special pairs with P1, PD minus 1 spanning the hyperplane H. So this set of elements in the Steinberg H module is a generating set. So generates Steinberg H as a vector space. And theorem dual is exactly the same statement, but once you apply duality. So now instead of a hyperplane, you have a line or a point. So L line. And then the set of, I won't repeat the statement, but the set that you take is PQ special. And instead of the first d minus 1 point spanning the plane, the condition turns out to be the first 2 points are actually equal to the line. So this common point that the two simplices had, actually you can specify it in any way you like, and then these together still span the Steinberg module. So they generate.
All of these theorems are for Q, right? Or some of them seem like they should be true for all fields.
The only place where Q matters is in the theorem about polylogarithms.
Yeah, but I mean, you use that theorem, right? You use that, for example, to have the generation set of Steinberg H.
No, I'm not. Okay, I'm kind of not using the theorem that I claim. I'm trying to explain how to prove the surjectivity part.
So
the surjectivity
it's really more of a opposite direction.
Yeah. I'm just saying the theorem tells you that this map is surjective, so it should be the case that Steinberg is generated. And I'm trying to show you why it's true if you don't know the theorem is true yet.
Okay.
Because this is a statement which has nothing to do with polylogarithms. It's just elementary projective geometry.
So I see. So you're trying to prove right now that it actually is generated by L.
Yeah, I mean, so these two.
Any field.
Yeah, so this is true over any field, not over PID. So that.
I agree.
Okay, so and either of the theorem or theorem dual will give this statement because it's weaker. So here we impose some additional conditions.
And do you think it's not true as a abelian group?
Okay. I mean, these I don't know. This is certainly what this is what I meant as a conjecture, I guess. Because you have to replace this by what the causal dual would be.
Oh, no, I meant like coefficients in Q.
No, yeah, I think the Q coefficients don't matter at all, so everything should be true still over with integer coefficients.
Okay, yeah.
None of these statements are sensitive to coefficients. And we're just trying to give proof of the theorem and then talk about the most interesting part. So the proof is, I mean, it's not very exciting to follow, but it's kind of fun to do yourself. So, and I will do it by just drawing pictures. Which is always nice when you can prove something non-trivial by just doing simple drawings. So what we want to do roughly, and I'll do it for d equals 3, you have an arbitrary pair of simplices in projective space. You want to apply some kind of sequence of relations in Steinberg modules in one or the other to reduce it to a picture. So we'll do it with, so this is theorem without dual. So this is our hyperplane. This is a pair of simplices in general position. We want to apply some sequence of operations to get this picture. And this will be still the same hyperplane we chose. And so there will be a few very simple operations that one can do. I mean, there's not that many moves you can play in this game. So actually, if you just try to prove it for 15 minutes, you'll prove it. But let me do it, at least one of the steps. So what you do is first, you want to replace both of these simplices individually by something which has this hyperplane as preferred. So this is an operation you can do separately, and it's kind of, in this particular case, it's easy to draw what's going on. So you take all of the intersections with this plane H, to intersect the sides of the triangle with plane H, which is a line in this case. And so you take this simplex and you apply the scissor congruence relations in the Steinberg. So you have to take the big triangle here with a plus sign. You have to take the long triangle with a minus sign, and you take the small triangle with a plus. So there's kind of 3 triangles formed, you can see in this picture, and this simplex is equal to sum of these with coefficients. And all of them have H in a special position. So that's step 1. Step 2 is we apply this operation to both yellow and blue triangle. So we land in this situation. I forgot which one they're all. I think the blue one was the inner one. So we get some kind of picture like this, and it doesn't matter whether this is exactly the location, so the order doesn't matter. And so what I do is next, I draw a line through, maybe it's a white line, through these 2 vertices. So the only vertex of the blue triangle, which is not on H, and the only vertex of the yellow triangle, which is not on H. I call this point something, maybe S. And then I replace the yellow triangle by, so I split it with respect to S. So I get 2 yellow triangles. And the pictures for the 2 yellow triangles are completely symmetric, so I just have to deal with one of them, but I'll just copy the picture here. And so at this point, we kind of keep the yellow triangle as it is, and then we do the kind of induction in this hyperplane. So now in a hyperplane, we have a pair of simplices of lower dimensions, which are just pairs of points. And what you can do is if I gave you the proof for 2-dimensional case, you just apply that proof in this situation. So it's, you replace, I think the blue, okay, so you replace the blue triangle by a difference of this and this. So okay, maybe let me leave this as an exercise to finish the proof. After that, after you do this case, actually the induction is very, very easy to work out. So if you do the 2-dimensional case, it doesn't tell you much because it's too simple. And the 3-dimensional case, well, I mean, the projective 2-dimensional case is just enough to give you the intuition for the. Okay, so what are the consequences of this result? And now this is maybe the more interesting part. Slow calories. Well, one of the corollaries is we proved surjectivity. I mean, I haven't talked at all about why this map is well defined at all. That's a long story. So, don't remember how I numbered the things anymore. So now it's really about homology. Okay, so the theorem, and I hope no one will mind that I put on only the well-known abbreviation for the authors. So it's Latius, Coopers, and Randall Williams. And I guess it's in their case, this field of the ring of coefficients is Z, but I'll state just a rational version. Keep as a D. So this homology group, so the coinvariance of the action of GLTZ on Steinberg L is one-dimensional. This space is one-dimensional. And so it almost trivially follows from what I said, except in the theorem or theorem dual, we allowed all special pairs, including degenerate ones. And on special pairs which are non-degenerate, the generic ones, the GLDQ acts transitively.
Should this be an H instead of an L?
Oh, yeah, sure. Sorry. Yes.
Do you mean GLD of the integers?
Sorry?
Do you mean GLD of the integers?
Yeah, oh, sorry, no.
That would make sense.
Yeah, no, that would be wrong, probably.
Yeah.
Well, for integers, certainly it's not true, but yeah. Okay, so how does the proof go now? Well, this almost tells us that everything is spanned by generic special pairs, except there are some products. But the good thing is actually if you apply the shuffle product formula, it allows you to rewrite any product in terms of generic pairs. So theorem dual or theorem implies that Steinberg H, well, I mean, okay, so Q can be any field. F D is spanned by L V1 VD, and on these elements the group acts transitively, obviously, because this is just the action of the matrix of these columns on the one of the generators. So we can get at most one-dimensional space of invariance. So the only ingredient that's not here is there is a, so the map from Steinberg H to VD, VD Steinberg V, which you compose with augmentation to Q is surjective, and it's GLD invariant. So you get one dimensional coinvariance, so that's it. And I mean, it's kind of nice that you get this result almost like by just doing elementary things. Okay, so
Can you recover the Steinberg Lie is 0?
yeah, I guess so. You just have to check that this coinvariant gets. And let me think. Maybe I think it's true. I just don't remember the argument. You just have to produce at least one relation with a minus sign in the Steinberg Lie. In fact, I think this should imply that in the Lie algebra it's 0, because I think it's sum of.
What is BD Steinberg?
It's the bar construction applied to Steinberg.
Should it be? Oh, I see.
It's
Not the D bar construction is just the bar construction.
just the bar construction, but to Steinberg, not H. Yes. Okay, and then. I mean, I'm not saying much because I don't have much time, but I want to say at least formulate the theorem due to Cooper's, Radchenko, and Lille. I think Ismail will talk about it later in the afternoon in much more detail. but not from this point of view. So phi, what you get is a map from H1 GLDQ. Well, okay, again, GLDF with coefficients now in Steinberg L of FFD. So you get a surjective map L, D, or F, which is a lot more interesting than the previous thing. So it's now, this space is actually huge, and not only that, it maps to what we think is the motif. Okay, so this is a theorem. I mean, this is Cooper's theorem. So what I want to say.
What's the right hand side?
The right-hand side is the this weight component in the motivic Lie algebra, or in my notation, it's the one that I defined combinatorially.
Oriel version.
Yes. So it's still a huge space with a lot of structure. And so I want to explain the map and explain why it's well defined. And the curious thing is that a priori this construction doesn't use any of the toric story. But to prove that it's well defined over Q, you can use the toric story, and it's a very conceptual proof. Okay. So I'll just tell you what the map is. And be careful. So okay. So basically, so I want to say, in the theorem that we had before, we had a map. Okay, I'll do everything over Q. I won't talk about the general case. So when you specialize the theorem that we had before, the theorem about map between polylogarithms and Steinberg module. So when the weight is equal to the depth, there was no symmetric power part, so that part is gone. And so here we have.
So LDL is LD modular product, is the indicopose.
Yeah. So this is like the LD modular products, and this is the indicoposes in the Steinberg module. And so there is kind of complex here. It's an exact sequence, I guess. So this map is surjective. There is exactly one generator for the GLDQ module here. So this is basically GLDQ times E1, 1, S1, S3, and there are some relations here which I haven't said anything about. So it turns out that there is a subset that you can pick here, which is actually almost a basis. So this is it's not quite free, but it's almost a free module. So to compute covariance, I mean to map something from covariance here, you basically have to define a map from the covariance on I into L. So you want to say how to define a map from here into LB. Of Q.
Sorry to interrupt. Why is there a kernel? Wasn't your theorem that this is a bijection?
No, I mean it's.
It is symmetric.
Yes, right. So this is kind of. I think I messed up everything. So this is not that. This is, let's call it formal, and I'll call this thing formal. So you just write down such a thing, which you think of as a free GLDQ module. And here you write all of the relations that come from the map. Sorry, that was a mistake. So then it's actually free, and then the relations are here.
I think Eric's confusion was that there was an isomorphism between the middle part and Steinberg H tensor symmetric power.
Symmetric powers.
It's something completely different on the right-hand side, right?
Yes, so symmetric powers are still there. It's just a zero symmetric power, so it doesn't appear.
Okay.
It's the case where the weight is equal to depth, and that case So in the formula it was symmetric power n minus d. In this case, there's no symmetric.
Also, in the middle thing, there's actually Steinberg H goes to Steinberg L, and then you have a kernel.
Yeah, I'm kind of jumping over details.
Sorry. Yeah, please
Just
keep going.
to find
My bad.
something not trivial, and then maybe you can ask questions. So basically, what I want to say is, what this object is a space of relations between these elements. So what we want to do is we want to find some kind of map from relations between polylogarithms of this type into the equal to the P, or the polylogarism. And we want a map which would be GLDQ. So that would be enough. I mean, if we can produce a surjective map like that. And so the recipe is you take any element like this. So you take you take I formal of a collection of vectors V1, Vd, and you map it to an element which is IL of infinity, and then you just write something. And where phi is some element so in some way some functional, and you just formally send any element like this to an element which does give the Q. And so, this map depends on the choice of phi, and there's nothing you can do about it here. So what we want to prove is if you take an image of any relation among these formal symbols, the resulting map will not depend on the choice of phi. Okay, and there is a basic way to do it. If you recall what the functional equations looked like in the LD of TD, so what the elements looked like. Definitely won't explain everything. So we want some, well, the map is here. We just want to check that if you get a relation between this element and the Steinberg E, the resulting map will not depend on the choice of phi. So that's the only thing that depended on some kind of additional data. And so how to prove this? So let me say, so let's consider some I formal of V1 I V. Let's say this is an element in I, not just call this thing. So this would be a matrix AI. So this, by the kind of the isomorphism between Steinberg module and the polylogarism space that on a torus, this would correspond to an identity between polylogarisms on a torus. So there will be some kind of sum like this. So I'll write it first with notation I said before. Is zero in LD of this huge field, which I don't have the notation which is good, so it's some field containing all algebraic functions on the torus. This is an actual identity except modulo lower depths and some other stuff which I rolled out at the very beginning. So it's almost an honest identity. It's very similar to the one I gave before in depth 2. And so what you can do is, so given your functional phi, take phi of EI is AI, and you consider a limit as some, I want to specialize this equation somewhere. So I want to take x1 to be ta1, xd to be TAD, and I want to take t going to 1. And so the non-trivial thing that's happening there, that these functions at the point 1 are highly singular. So actually, the limit will depend on the choice of the parameters A1 up to AD. So there's two cases. So if you take kind of the limit of e to the A1, e to the AD 0, and t goes to 1, so this should be some kind of specialization map. So there is a calculation that you can do that tells you that this is actually, again, a multiple polylogarithm or iterated integral, but on the exponents of these functions. And these are exactly the values of phi of E1, phi of ED, so that you can see the relation between the construction and this. And so this is not quite what we have in this idea. So if this were the case, we would apply this limit. We will get actually the sum of these numbers would be 0, which is opposite to what I'm saying. So it should be non-trivial map. So it's not quite true that there's only these limits that appear. So there are also limits which look like this. And that's because of all of the other roots of unity, like roots of monomials which appear. We have a bunch of terms which involve roots of unity. And in that case, the limit actually doesn't depend on AIs. Zeta 1, zeta z, 0. So basically, you take an identity and you apply the limiting procedure, and some of the terms in this identity produce functions of A1 to AD, and the other ones are constant. But you know the identity is true, so the sum of all of these terms plus the sum of all of these terms is 0. And now this is exactly the map that I defined there. And this is constant in A1 up to AD, so it doesn't depend actually on the choice of phi, which is a very strange way to prove it, but
D, should it be row lower D there? In the left? Zeta?
No. Here.
On the left.
This is lower D.
Yeah, and
On the left as well.
Yeah.
I see. Those are just random.
Yeah, these are some roots of unity. So
Not the powers. Yeah, okay.
Yes.
So is this the standard regularization formula?
Yeah, it's essentially, yeah. So it's some kind of a very simple specialization. So yeah, I'm done.
So why does this limit not depend on the A's anymore?
So there's some kind of continuity of this function everywhere except diagonal. So if you specialize it to any point which is not highly singular, the limit will, there will be, so this limit, it's actually a specialization map in this Lie algebra. And it's well defined and it gives you this thing literally.
So you're not allowing the rows to be just all equal to 1?
Even if, no, yes, so here, yes, so not all zeta i's are 1. Yeah, otherwise we're in this case. So there's two cases, either every root of unity is 1, in which case we have dependency on the point, otherwise we don't have it. And because we have an identity, it kind of proves that something is constant function of AIs, which is a non-trivial identity in LD. So actually, by this process, we got a non-trivial functional equation in the motivic Lie algebra as a byproduct, just by doing this calculation. And so you start with something on a torus, and you get essentially a very general functional equation. The only kind of problematic part here is that I think I have to take AIs to be integers, and the whole story actually only made sense for the field Q. So this only explains this construction works well for rationals, but it's kind of a formal construction, so you can prove that it's well defined anyway. So I don't know if Ismail is going to talk about it more. But yeah, okay.
Comparing the two structures, so what happens with the co-bracket on the Steinberg set?
Well, that's not in my paper. So you mean what is the co-bracket here?
It's in your general theorem. You had something about polylogs relating it to Steinberg H. On the polylog side, you have the co-bracket.
Yeah, that was the part about the VB Hopf algebra structure. So on Steinberg, on Steinberg H there is a coproduct in the VB sense, and there is on Steinberg L there is a cobracket again in the VB sense, and they're all compatible with this map. So if you properly kind of define what a cobracket in this LNTD, it agrees.
But you're not using that anywhere.
I mean, in the proof we use in the proofs we use it, but I mean for the presentation it's not here. There is more structure that's not I haven't talked about.
Otherwise, thank you again.